Okay. So this week is, as I was saying, this week's the last week of homework. The rest of the course is going to be, at least these Zoom sessions are going to be focused on review and getting you ready to do the final exam, which is going to be like a big take home project. Uh, Very similar to the homework. So we'll just have a bunch of homework style questions on it that you guys will have like a week to do, and then you'll hand it in at the end of that week. So a lot of fun. But yeah. Uh, all right. So this week, what we're going to be doing, and especially this class, is I'll be introducing a new language. So I know a lot of you guys were writing me and telling me that TFL seemed too simple, you know? It couldn't do the things that you wanted it to do. Uh, and didn't have these really nice modern features of modern predicate language. So that's why this course has you guys learn first order predicate logic, or AKA FOPL, which is what this acronym FOPL stands for. So first order predicate logic, why is it called that? Well, I'm going to show you guys something about TFL that might make you unsatisfied with that language. All right. We've got an argument here. If you guys remember, arguments are a series of assertions, one of which is the conclusion, which we have down here, and the rest are premises. So let's try and translate this argument to TFL and see if we can figure out if it's valid or not. All right, all Canadians look like muffins. Well, I guess I'll use the predicate M to stand in for looking like a muffin, and C, the name referring to Canadians. All right. Well, this second sentence, Justin is a Canadian, if we're going to translate it to TFL, we're going to need a new predicate, right? Sorry, a new property, being a Canadian, which is capital C. And then a new name, Justin. Because this is a different, it's asserting a different, much different fact than the first sentence, right? The first sentence is the object is Canadians, and the property being asserted of them is looking like a muffin. Meanwhile, in the second sentence, Canadian isn't an object, it's a property being asserted to an individual. All right. Last sentence, the conclusion. Justin looks like a muffin. All right. So we've got capital M as that predicate looking like a muffin, and then little j is my name. Well, yeah, the name referring to me. All right. Is it so? When we look at this argument, all Canadians look like muffins. Justin is Canadian, therefore Justin looks like a muffin. It's intuitively valid, right? So if both of these are true, it seems like the conclusion has to be true, right? There's that truth preserving matter of fact between the premises and the conclusion. However, in translating it to TFL, we wouldn't be able to derive this. Maybe we could show that it's valid using a truth table, but derivations wouldn't be able to show this. And also, it seems like the translation can't capture the meaning of this argument, right? It's not really, this translation is not really capturing what's going on when we move from these premises to the conclusion. All right, but if we add some things to our language TFL, we might be able to capture what's going on in these assertions. All right, and this is, by adding new things, we're going to make a new language. And this is what we're doing for forced first order predicate logic. We're adding two new things to the language, variables and quantifiers. So just the variables x, y, and z, and the quantifiers, the sort of upside down a and backwards e symbols. And here's what they're going to do in our language. So variables are going to stand for something / anything. We don't know what, it's just like a variable in mathematics. It can be any number. It's a symbol that stands in for any, for example, names in the domain. So maybe we have like a domain, if you remember these models with all the Canadians. So when we use a variable now, X could be any Canadian. We don't know which one. It's just, it could be any of them. All right. Quantifiers are then what tell us how many things the variable applies to in the domain. So the upside down A means all of the things. It's the universal quantifier. All things. Or at least one of them. So the backwards E is called the existential quantifier. And it's sort of equivalent to saying some. Okay, and so what this is going to allow us to do, if we just go back to this argument, it's going to allow us to do something like this. So we get to now make a bit more of a complex assertion to stand in for assertion 1. So it's saying that there's, for something that is x, I want to use C. Sorry, that's supposed to be a C. There we go. For all x in the domain, if it's an x, if it's in the domain, then it's Canadian. And if it's Canadian, then it looks like a muffin. So this is now what FOPL lets us write down, because FOPL lets us talk about categories and represent assertions about categories of things, like all Canadians or all numbers and such. And you're gonna, on Wednesday, I'm gonna go more into detail on how it does that and how we can do that using FOPL. But all I want you guys to get a handle of now is that adding these new elements, the syntax, variables, and quantifiers is going to really open up the amount of things we can translate from English to a symbolic language. 2 is going to be existential x, something that's Canadian, and then the conclusion, therefore for something that's Canadian. If it's Canadian, then it looks like a muffin. And so what we're not going to cover, unfortunately, since there's only so much time in this course, is we won't be doing derivations with FOPL. You guys are just going to learn about this language. But FOPL does introduce derivation rules to go along with these new parts of a language. So there's a rule for adding existential quantifiers, getting rid of existential quantifiers, turning them into universal quantifiers, and so on. But we won't be doing that. If you guys are interested in doing those sort of things, then taking the Phil 115 is what I would recommend. Okay, so the syntax of our new language is what we're mostly going to cover today. And then later this week, we'll talk about the semantics, what these sentences mean in more detail. But the syntax is important. So in any case where we would have a name, so a lowercase letter, we can replace those names with a variable. So for example, we can have multiple variables in an assertion. So we can have f of x, we can also have a relation like gxy, or even, 4 variables and names combined with each other. So if you think about, like, n might be the property of being a number, and we might be asserting, all x's are numbers, and also the number 1 is a number, where a refers to 1, right? Okay, so the way that these quantifiers work is sorry, I lost track of where I was. All right, but trying to stay on track of syntax here, because it's so tempting to just talk about what these things mean. Okay, quantifiers appear at the beginning of, or to the left of the well-formed formulas that they quantify over. In the same way that a negation symbol appears to the left of the well-formed formula it negates, right? So you can think of quantifiers operating the same way as a negation. If a quantifier is outside of the brackets, then it's going to quantify everything inside the brackets. If it's inside the brackets, then it's going to quantify the well-formed formula right next to it, like this guy. So the way to interpret the quantifier slash variable relationships is the quantifiers tell you which things the variable applies to in the domain. So they sort of set the truth conditions for those sentences. So it's not going to be a simple matching relation. If you guys remember models from before, we would specify, A refers to muffin, and then in the predicate M, there'd be an extension, and then we would see if muffin is in that extension. With variables, it's not as simple as that. So we'll be going into more detail later, but just to say that a casual reading of these sentences is that we don't know what exactly is a muffin, but something in the domain is a muffin. So X could be anything. We just know there's at least one thing in the domain that has that property X. I mean, that property M. Okay. So the alphabet changes for FOPL significantly from TFL, but not too not too drastically. So we still have predicates and names. We're just adding variables and quantifiers. And of course, with the new alphabet comes a new recursive definition for making what counts as well-formed in our language FOPL. Before I go into this, do you guys have any questions so far? Okay. So our well-formed formulas in FOPL are any predicate followed by any finite sequence of names and variables. So that's similar. The only difference here from TFL is adding variables to the things that can be in that sequence. And then this is exactly the same. Same. This is different. Line 3 is different, and I'll underline the part that is. So W be any variable, then each of the expressions are well-formed formulas. Oop, got a question. Aaliyah can't see the screen anymore. What does it show instead of the screen? Oh no. Okay, can the rest of you guys see the screen? Okay. Geez. Why is this being so buggy today? All right, let me reshare. Huh. Hmm. Well, I'm going to post these slides soon, Aaliyah, so you can check it out on Blackboard. And I'm almost done. So once I'm done, I'm going to also upload this slide to YouTube. So today's a sort of brief lesson. All right, so right, the differences in these recursive definitions. This number 3 part makes it so it tells you how to make compound expressions out of quantifiers. So in order for a expression to be permissible, the quantifier has to be to the immediate left of some variable. So a variable, anything has to be in that any variable has to be in that W spot, and then any well-formed formula has to be in that P spot. So after the variable has to be some TFL well-formed formula. All right, so it's not a huge drastic change. We still have all the same compound well-formed formulas. We just are adding these expressions, these quantifiers to the left of variables. So if you think about how the quantifiers are telling us what the variable applies to in the domain, it makes sense that you have the quantifier, the variable, and then the well-formed formula that it's modifying. Okay. And so here's some examples. I'll just go through these like, so actually I think these are in the homework, so I won't go through them. But these are some example well-formed formulas. You can have as many quantifiers as you want to the left of a well-formed formula, because this schema here makes it so that any number of well-formed formula can be inside of the P, and even ones that have quantifiers in them. All right. So that's it for the syntax, the basic syntax of FOPL. On Wednesday, I'm going to cover more complex syntax concepts, and then on Friday, and also a bit of the semantics of FOPL, and then on Friday we'll go into more semantic detail on how to express assertions using this language, like complicated assertions about categories and such. And it's really interesting because this is really the language that logicians in the last century used to study things like mathematics. Because if you think about it, this expressing facts about mathematics, you really have to, you're expressing facts about categories of things mostly, right? Numbers themselves are categories. So in order to express facts about mathematics, you have to have these tools to talk about categories of things, which is what FOPL does really well, where TFL really doesn't. TFL is a language where you can only really talk about objects. All right. Any questions, guys? No? I'll see y'all on Wednesday.